There you go. In fact, let's go and zoom in and see how well we are doing. Let's go in here somewhere. Let's go look. You're looking to see when that thing's going to fall off. That's the accuracy measure. Well, it just doesn't want to fall off. Doesn't want to fall off. You see what's going on over here? This is below 10 to the minus 5. Let's just try to make it fall off. Come on, fall off. Fall off. That's called spectral accuracy right there. Okay? By the way, look at our dx. This is what I want to highlight to you. The dx in this region where we were blowing it up was what? About 0.2. So if you were using finite difference there, you'd only expect an answer that's 0.2 squared accurate for a second order scheme. So, you know, your accuracy would only be like, what, 0.2 squared is like 0.04, right? 10 to minus 2. We were going down to 10 to minus 6, 7, 8. Nothing wasn't falling off. That's what spectral accuracy buys you. Much higher degree of accuracy. Here, like 8 orders of magnitude higher degree of accuracy. That's impressive. Only 20 points to get the whole thing. Okay? If I wanted 10 to the minus 8 accuracy, which is this basically is giving me, I would need to take my dx to be 10 to the minus 4. Right? So I need 1,000 points per 1 unit. So I'd need 2,000 points here if I was going to get the same accuracy. 2,000 points versus 20. Tell me which one you want. 20 is the right answer. Exactly. Thank you. All right, gold star. But that's the kind of thing you're looking at. Okay, this is why people like Cheb. It's a spectrally accurate routine. 20 versus 2,000. Right? I mean that's easy math. Okay. Now let's do 2 derivatives. So 2 derivatives. That's pretty easy to do. Then you just take, if you want the second derivative matrix, let's call it D2. For the second derivative matrix, it's just D times D. Or D squared. Okay, and then we can get U2xx is D2 times U2. Then we can plot that. Subplot 3, 1, 3. Plot x uxx. Again, black line. x2 u2xx, which in circles, and now we have derivative, first derivative, second derivative. Okay, there you go. 20 points I can do this in. Pretty remarkable, pretty nice. There it is, doesn't care about boundaries. Very general way to handle boundaries, actually. It doesn't care. It doesn't have to have no flux or fixed or pinned or periodic. It just says whatever the boundary is, I'll handle it. Your constraint, -1 to 1. Or scaling of it. Okay? Okay, so that's differentiation. So if you want a good differentiator in life, this is it. That Cheb polynomial matrix, or this D matrix. Yeah. Yeah, it doesn't care. Okay? So there you go. And the nice thing about it, you don't have to define the x ahead of time. You just say, how many points do I want in there? 20, 30? 40? It's a dense matrix, by the way. This is one thing about it. One thing about this is this matrix D, it's a 20 by 20, but it's full. Remember in our differentiation matrices before, they were sparse, right? You use only your nearest neighbors, so there's a bunch of zeros in there. And you had just a few diagonals that mattered. The whole thing's full. Okay, that's the drawback. Because you're working with full matrix now. Okay? All right, now, let's use this to actually solve some problems. Okay, everybody like that so far? Everybody good with that? It's kind of cool. We just differentiated something. Prefunct's picking up a little bit now after a quick hiccup in the road. All right, let's start with that. So let's get back to the board up here real quick. And I'm going to do a little problem today in class, which is going to be a lot like what you're going to do in your homework. Okay, so this is good. So let's solve the following. Heat equation. By the way, your equation looks similar, right? It's this plus stuff. This stuff you're going to add is, okay, it takes a while to type it out, but that's not that big a deal. The question is, how do you handle this? So we're going to solve this right now. So this is going to be ut equals uxx plus uyy. So first of all, I know how to do derivatives. You know how to do derivatives now, right? I mean, we just did it with the Chebychev polynomial. We said, oh, if I want to take the derivative of this, I got to just multiply. This is like that d squared matrix. Give me that, right? And then I'm going to have a derivative in x and in y. So it's just like Fourier transform. There's this idea that there's this directionality of the kx's and the ky's, two-dimensional. We have to set that up. So we'll do that. And then you're going to learn a super awesome command. You ready? It's so awesome it even has an awesome name. KRON. I know, isn't that powerful? Do I look bigger when I say that? You at home can probably see I'm getting bigger. KRON. Okay, remember that movie Kroll? If you're old enough, I'm talking about the people who know Justin Bieber. I'm talking about people like, you know this movie Kroll, which is a dude movie. And that's the guy's name. Anyway, his big sword and kills people. KRON is kind of like that. Okay? KRON kicks it for you. And then you'll be a little disappointed that I didn't teach it to you earlier. Because KRON allows you to go to 2D really simply, without thinking a whole lot. Okay, and I made you build these matrices and put down SP diex rows and figure out, oh, is it this row or this way? Oh, how do I do this? You know those ABCs that you built? This just sort of does it for you for free. That's okay. You were not ready at that time. Now you've proven yourself worthy to use the KRON command. Okay. So we need a 2D matrix for differentiation, and that's what we're going to do with this guy. Okay, so let's come back here, and let's start building this thing. So first of all, we're going to start this thing off. Let's stay with 20 for now. And notice, when I do this, there's no sense of directionality. Right now, I have a differentiation matrix, right? Just you apply it to some vector, and it thinks it's 1D. Now we've got to go to 2D. And so how do we go to 2D? Well, the first thing you get out of here is x2. And x2 is basically this quantity, which tells you how x is split up. Well, let's call it x now. We don't need to call it x2, right? That was only because we had an x already. So with x, well, we'll just make y equal to x. It's going to be chopped up the same way, 20 points. And now we need to give it directionality, and there's no difference than what we did before. Mesh grid it. Done. No dent. All right. So we mesh gridded it. It now knows that x and y is this grid of points, right, that are in 2 dimensions. And we'll need an initial condition. So let's go ahead and figure out some kind of initial condition we want. And you know what? It's always easy to start off with something like a Gaussian. That's the oldest trick in the book here. And by the way, I'm going to divide by here to make it a little, because I'm in this domain -1 to 1, right? I haven't rescaled anything. I'm just going to assume I'm going to work on a domain -1 to 1. And I'm going to say P color, X, Y, U. So I want you to just see this in 2D. Okay, there. This is what we want to look at. So this is obviously not very well resolved, right? It only took 20 points. But I want to highlight a couple things to you. What does this grid look like? So what you see is it's fairly large boxes in the middle, right? Pretty big dx's and dy's. But what happens at the edges is the clustering and the clustering. So your scaling or your resolution of your grid gets very nice towards the edges, not as good in the middle. Okay? So always remember that when you work with Chebychev points, this is the generic thing that you're going to start working with. Okay? Now, an important thing. Sometimes you might do the following. p color u. Now, why would you do this? Well, normally, you'd say, I'll put in my xy coordinates. Who cares? If it's on, so if it's evenly spaced points, p color u and p color with xyu will look the same. But now, when you do this, here's what it looks like. And this is wrong. If you don't put your x and y in, it assumes that you're working with evenly spaced points. And then it gives you this, which is like, oh, look at that. It's a square domain and equally chopped up. This is not what you have. Okay? So when you do this plotting, you have to always remember to bring back your x and y back in, or else it will warp this. In other words, it's stretched out the boundaries for you. Because it thinks all the dx's are the same. They're not. Okay? All right. So that's going to be our initial condition. We have our domain set up. We have our differentiation matrix. Oh, wow, we need a 2D differentiation matrix. And I need two derivatives in x and two derivatives in y. So let's make an operator called L. And L is going to be this matrix that does two derivatives in x, two derivatives in y, and it understands this directionality. Okay? Let's do this. Hold on. Okay. So first, before you do this, what you need to set up is this matrix here, I, which is a diagonal matrix of ones. Okay, you ready? Are you super? Has everybody got their seatbelt on? KRON is coming. Ready? Now, I want to take two derivatives in x and two derivatives in y, and here's what you do with that. Here is the KRON command. KRON, and you're going to say I d2 plus KRON d2I. And that is your 2D Laplacian. Simple as that.